Welcome to Hackster Café. My guests today are three people from OpenScope. So you built a new oscilloscope with some extra functions, which is on Kickstarter. What differentiates it from stuff that's already on the market?
One, this is open source, so you'll get to see all of the code. Another is this is a MCU based oscilloscope. There's no FPGA, there's no external ADCs, everything is all based on the MZ. There is a few analog components, but not very much. It pretty much is all done in firmware. And, you know, it's pretty impressive because it keeps the cost way down. Plus, the way we actually get precision and accuracy is through the firmware and calibration. We don't depend on the hardware actually being of high, super high quality. We calibrated all of the inaccuracies out in firmware.
Wow, cool.
Yeah, so one of the goals for the project was to have something like, so generally Digilent designs equipment for engineering, so engineering education, like for electrical engineers. And so an oscilloscope and a logic analyzer, that's, kind of the standard tools for an electrical engineer. And we wanted something that was affordable so students could own it, but capable enough that you could get away with doing most of your homework assignments with it. And so we're shooting for really low cost and fully open source. So hardware, firmware, all protocol, communication protocol, and everything is all open source. And so to Keith's point, to do that, we're using a PIC MZ from Microchip as the core of this device. There's no operating system running on it. It's all bare metal. Just run the firmware that Keith created. And it's actually programmable in the Arduino IDE. So you can add it as a target and customize the firmware there. Yep.
Well, it's being a PIC.
Yeah, it's programmable in the IDE. It's also programmable through MPLAB-X. So you get full debugging. If you go to MPLAB-X, you'll get absolute full debugging capabilities that the IDE would bring you. But if you're just, somebody wants to not have to buy any hardware, or they just want to download the software, download the IDE, and then you can program it through the Arduino IDE. I do have to qualify that you'll have to use a specific Arduino IDE and a specific core, because as the IDE, especially as Arduino moved forward, they broke some things. So, so we will be enumerating specific cores and IDEs to download for it to work, but it will work.
Cool. What kind of stuff can you do with Arduino and the OpenScope?
I mean, you can completely compile it. You can program it. You can, if you want to, you can attempt to change the code to do your own thing with it. Cool. All the code is there for you to play with. There's a lot of code, and it is pretty intense. So you'll get, if you're going to change the code, you're going to get your hands dirty.
So the firmware that we ship on the device will also have as just an Arduino IDE project, right, Keith?
Yes, in fact, the way that the project is structured as an Arduino sketch, and MPLAB-X actually builds out of those sources. So if you look at the sketch directory, you'll see an MPLAB-X project directory, and then you'll see the sketch directory with all the sources.
Legit. And in the meantime, I imagine that you're not only driving down the cost, but you're probably making it a lot smaller by eliminating extra components like ADCs.
Yep. Yeah.
There it is.
Yeah.
Oh my God! Look at it. It's so small.
Yeah.
Yep.
Cool.
So Keith, in addition to doing all the firmware, did the hardware design on this as well. And we were talking about some potential changes, but yeah, that's one of the things that always comes up is keeping it small, the kind of thing that you can easily chuck in a backpack and maybe in your back pocket, as you're walking to class.
That's a far cry from the one like. Have you ever tried putting one of those giant plastic handles on it just so you could
lug it around?
You can have like 20 of those in one of them.
This is the 3D printable case for it. So you can just download this and print it, and then you can put your OpenScope in there.
And that's one of your Kickstarter rewards, right?
Yeah, but we'll publish the file, so you can download this and print it.
Oh, cool.
Yep. All right, so what we're going to show you here is the Waveforms Live software. So that's our browser-based instrumentation software that we use to communicate with the OpenScope. And the other piece of that is the Digilent agent. So the Digilent agent you install on your computer, and it just runs in your system tray. And that'll be available for Windows, Mac, and Linux. And that basically bridges from your browser to the hardware. So we can do cool things like set up the Wi-Fi on the device and load firmware and things like that through that agent. So Darshan has Waveforms Live open here, and you guys can all play around with this today at waveformslive.com, and you can play with our beta software. And then if he clicks Add Device at the top, he has the option to add a network device, a simulated device, or the agent. So a network device would be if you're going to connect to the OpenScope over Wi-Fi. It has a Wi-Fi radio on board. So you just hit network, and you can type in the IP address and the port to connect to it. This time we're going to connect to the agent so we can show you some of those features as well. So hit the agent, and the agent just acts as an HTTP server. So you type in, again, its IP address and that port, which it automatically loads in for you. And then they'll hit that plus button, and he'll add an agent. So this will then enumerate all the devices on his, all the OpenScope devices connected to his computer. So right now he has an OpenScope MZ connected to his computer via USB, and it's showing up as COM3. So once he's connected to that, then things like the Wi-Fi settings and calibration below will fill in. So if you look all the way down at the bottom, he has the option to calibrate the device. So this is what Keith was talking about, where we make up for using less expensive hardware by doing calibration on the device.
Yeah.
So when he clicks that, you get the calibration wizard, and it gives you instructions on the connections you need to make to do the calibration. And Keith will talk a little bit more about what's actually happening here later. But you make connections, just the device to itself, and then it's going to run through a series of calibration steps and calibrate all the instrumentation to make sure that things like temperature and humidity and stuff like that are all calibrated out. So it'll take just a couple seconds, and when this is done, then you have the option to, so you can see the calibration data, which is returned, and you'll have the option at the bottom to save this as either the factory calibration or the user calibration. So we calibrate it once before we ship it to you, and that's the factory calibration. And then you can save it as a user calibration to use all those offsets when you're actually acquiring data. So he'll go ahead and hit save there. And that's saved on the device itself. So if he unplugs it and takes it to work and uses it there, that calibration information is still saved in the device itself. So then if he hits done, the other thing we'll look at here is the Wi-Fi settings. So we're showing you currently, you can see that the Wi-Fi status is connected. So he's connected to his home network, and we're printing out the IP address and SSID there. So it's a good place to go to see, find the device on your network, see what its IP address and things like that are. And then if he hits the setup Wi-Fi button, this will walk you through the Wi-Fi setup on the device. So you can select from saved networks. So you can see he has the digital network, so the work network and his home network saved there. And he can just click to connect one of those, and they'll automatically connect if they're within range. So that's why he's on the digital or his home network right now.
Yep.
And then if he goes ahead and hits the scan button under available networks, we can actually scan for the networks that are available in his area. And then you could choose one and connect to it if you so wanted, but he's already connected to one. So you can click one and maybe just see what it looks like. Basically, just give you the option to put in your password. We'll show you all the other information. And then under the advanced options, we'll let you do things like connect automatically if it's within range, or connect right now or not, things like that.
You mentioned that you can have multiple of these connected to a single machine. Is that true?
Yep. Yeah. So you could have as many as you want really connected via USB, or just spread out throughout your network. Just as long as you're on your Wi-Fi network, you can connect to them. And like Darshan and I were talking earlier this morning, the agent, since it builds for Windows, Mac, and Linux, we haven't tried yet, but we plan to build it for devices like Raspberry Pi. So you should be able to run the agent on the Raspberry Pi and USB connect the OpenScope to the Raspberry Pi. But you could also just fire up the browser. Basically, anything that has a web browser can connect to the OpenScope via Wi-Fi, which is pretty cool. So you can do things like take your phone and connect to the OpenScope anywhere that you have a Wi-Fi connection.
Yeah, this does look like a pretty mobile-friendly interface.
Yep, and so it's all built using Ionic 2, and Darshan could talk more about that if you're interested. But one of the cool things about that is it lets us also build this as a native app. So you can fire it up in the browser without installing anything, but we'll also have apps for Android and iOS that look exactly the same.
So if we go back to this main page here, we can see that the device that we added is here as a card. You can click this More button to get back to the configure page where we just were, or you can connect to it. You can also just click the card to connect. So this will take us to the instrument panel. So on the instrument panel, I guess we'll start with getting a buffer of data. So we can turn on the wave gen here. We'll just generate a 1 kilohertz sine wave. You can change whatever type of wave you want here. So we can toggle that on. And we can actually see the wave gen, or the wave that we've generated, if we connect the oscilloscope back over to the AWG, so a little loop back. So if we hit single now, this is a buffer of data from the OpenScope. You can zoom in with the mouse wheel. You can also pan. The timeline shows like your view in the window. So you can see this is where you are, and you can click in the timeline and kind of drag that around. On touch devices, you can also pinch to zoom. So that makes it a little bit easier to navigate. We also have some math functions. So if we click down here, you can see the calculated frequency is 1.001 kilohertz close. You can see period, amplitude, peak to peak, all that good stuff. And you can actually click these buttons and it will pop these down into the chart. So now you can dismiss this and you can see this information here.
Oh, cool.
And if you have a new wave, say you wanted to generate like a 10 kilohertz sine wave, you can click this refresh button and it'll recalculate that stuff. You can also open this cursor menu. So right now cursors are disabled. You can set the channels. Right now, oscilloscope channel 1 is the only channel that we have. And then we have 3 different types of cursors. So we have time cursors, which are basically like x-axis. Track is like x and y-axis, and then voltage is just your y-axis. So if we go with time, and then close this menu, you can kind of see down here the information of where the cursors are. So you can click these and move them around. So we can put one on this peak and the other on this peak, and we can see the time values and voltage values associated with those cursors. You can also see the time between them. So basically 1,000 microseconds, and then the frequency, if you're going to calculate it based on the difference in time, would be 995 hertz, or close to 1 kilohertz. So that's what we would expect. We also have some other interesting things. We have digital down here. So you can, right now they're all set as inputs, so we can actually read those. So right now those are all read as high. We have an analyzer. It's not in the firmware yet, but it is supported in the hardware. We can also change the direction here. So we can set like channels 7, 8, and 9 as outputs. And you can actually click these buttons and set them high and low. So if you had a little LED, you could turn that on and off. And then just click these again to set them back as inputs, and you can read again. We also have a DC power supply. Keith can talk a little bit more in depth about, on how the DC power supply works. But you can set something to, say, 2 volts, and we can set channel 2 to like, maybe let's do like 100 millivolts. And it'll actually read those voltages back to see what it's actually set to.
Cool.
Yep, that's pretty much the main stuff for the GUI. We can go back to the device manager page here.
So how come it's reading 78 millivolts when it's set to 100? Is that like a weird thing of how the reader works?
So it's reading back what the value was set as. So when you set it to 100 millivolts, again, Keith should probably be the one explaining this.
Yeah, so the resolution on the power supplies is about 41 millivolts.
That's right.
So 79 was the closest value that it could actually hit. Yep. So when you choose 100, the browser tells the OpenScope, hey, set to 100 millivolts. And the OpenScope then figures out what it can do that's closest and sets it to that and says, hey, my actual value was the 79 or whatever it was we saw there.
Cool.
Yep, exactly. So yeah, that's pretty much it for the GUI. I guess do we want Keith?
Do you want to show the firmware update?
Oh yeah, let's do that. So we can go and hit configure on our device again. we'll connect. We can click this button to update or load the firmware. So you can see our current firmware version is 0.41.0. It's also the latest version. But you can click this drop down and see previous versions. So if we wanted to load 0.36.0, we can click update. And what this does is it actually goes and grabs a hex file from a server, just a little Amazon bucket for now. And it grabs that hex file and actually posts it to the agent. And then the agent then uploads that hex file to the OpenScope. So it just finished uploading, and now we're reconnecting to the device.
And even, we kind of did this originally as a way for us, as Keith works on firmware and we're working on the agent, the browser side. We keep passing these files back and forth, and we quickly realized that, especially after we release and we want to do updates, this was like a really slick way to share not only browser updates we just push to our server, and when you refresh the page you get the update. But firmware updates now are like just as easy. You don't have to go find the file or anything. We can actually alert you when there's an update, which Darshan's going to show here. We'll pop up this little notification. Hey, we've got an update for your device. And then you can just click it and click next, and it'll download that firmware and load it. And you don't have to do anything else yourself.
Excellent.
Yep. So there, now we're back to the latest version of the firmware.
All right, should we pull Keith back on to talk about the hardware a little bit?
Sure, let's do that.
Yeah, cool.
Okay, so some of the questions that were asked, we'll talk a little bit about calibration of the device. So in general, the device is made with fairly inexpensive hardware. There's not a lot of analog hardware on there. There's a couple of op amps or for scaling the input, and really there's not much. The ADCs are actually on the MZ itself. There's 5 dedicated ADCs.
The MZ is the microcontroller.
Oh, the micro. Yeah, we were going to call the MCU the MZ. So it's a PIC32 MZ, the microchip processor. But on that processor, there's actually 6 ADCs. 5 of them are dedicated. Each ADC runs at 3.125 mega samples per second maximum.
Yeah.
But I've interleaved 2 of them, and we will get 6.25 mega samples per second on each of our analog in channels.
Wow.
So, and the way that works, of course, is to get the calibration is the 6 ADC is actually a shared ADC, and there's 46 inputs to that I can pipe into there. And what I do during calibration is I actually write a value out and then read it in the ADC, and I compare to what I expect it to be. And if it's not what I expect it to be, I adjust it. And actually, all of the instruments, all of the analog circuitry, all the DC outs, and to some extent, the waveform generator is a little different. What I do is I express all of the circuits as polynomials, and I calculate the actual coefficients of the hardware there, and then it dynamically adjusts for the hardware, and you get nailed dead on. What makes the OpenScope work so well is I offload all the instrumentation into the peripherals. And the CPU is not really doing anything when the peripheral's running. So when the function generator is running, all it's doing is it's DMAing a buffer out of memory onto the H port, and the DMA just runs. And the CPU's not involved at all.
Basically, all the samples that will be outputted are already set up in memory somewhere. So rather than generating a point and writing it out, and then the CPU generating a point and writing it out, and generating a point and writing it out, rather than that, we can go right from memory right out to the pin without the CPU being involved. So then the CPU is freed up to do things like service the network stack. So that's how we can make sure we're still responsive to the user interface while generating these really fast signals.
And that's how we do the sampling also on the ADCs. There are 2 analog in channels, and I told you I interleave 2 internal ADCs for each channel. So I'm running 4 ADCs for the 2 channels. And the way those all work is I just set up the DMA to read whenever the ADC is done converting. I just read that data into memory, and the DMA just continually just sucks in that data all in the background. And CPU's Doesn't care what it's doing. It just does that. And the only thing the CPU has to pay attention to is when the trigger fires. It says, okay, this is how long I'm going to run now, and then I can just turn off the timer, and that collects the data and spits it out.
So how long have you folks been working on this?
I've been working on this firmware and generation for about a year.
Yeah, we went through a handful of different iterations of the hardware. Like Keith said, starting with an FPGA and a microcontroller, and eventually figured out we could do it with just the PIC-MZ. We kind of originally had the concept for maybe an FPGA Shield add-on for like an Arduino or maybe like a Raspberry Pi or Beagle and Black, like hat or cape kind of thing.
Yeah.
But we eventually kind of just came around to the fact that it could be a standalone device. If we put USB connectivity and Wi-Fi radio on there, just the MZ by itself was pretty capable, and that helped get costs down. And that was kind of the goal of this project, was to make it student affordable. And the other thing that really helps is it's a lot easier to modify the firmware using the Arduino IDE than to have to install Vivado and write HDL and try to use an FPGA.
Right.
So we could have done that, but it makes it a lot the bar for modifying the firmware or anything like that a lot higher. So we were happy to avoid that.
It seems to definitely open it up.
And we have developed it's in the JSON language. We have developed a command protocol. You literally can control this thing from a terminal program. You just send it, ASCII commands, and OpenScope responds. When we talk to it through the HTTP server, we just put the JSON commands into a post, and we post that. And so it's the same command structure, whether we're coming in through the HTTP server or if it's coming in through the COM port. Or you could sit there at terminal, your favorite terminal, and actually type
by
it
hand.
Yeah, which, by the way, is how I do almost all the development.
It's all
if people want to build an API, it's super easy.
Yeah, well, that way I can, you can type in anything. So as I'm working on the next command, it's not in the browser yet, so I have to have some way of typing it in and getting it to work, which I do from terminal.
And all of that is documented on our wiki as well.
So you can write your own interface to it by writing to the JSON commands.
And also the language itself, the communication protocol, is pretty useful. So it's the kind of thing where if you wanted to, you could maybe take a Raspberry Pi and implement the protocol for it, so you could control its I/O through the same protocol.
Awesome. So what's next?
We're still
finishing the product.
So we're in beta now. We have a handful of features left to implement, and then a ton of stuff that we would love to implement. Like Keith said, we have the logic analyzer yet to go. We'd love to do like protocol analysis, arbitrary functions for the function generator. So lots of stuff there that we're eager to work on. We're kind of in the middle of our Kickstarter now, so we're starting to get feedback from kind of our beta users. So we're implementing that and working with them to kind of get direction on where to go from here.
So you already have beta people going. So as soon as the Kickstarter is out, you'll be able to start shipping, or? It's only a month out. So
we're not quite that fast. So luckily
I don't know. I got hardware right here.
Share that between the hundreds of backers. So one of the nice.
I got 25 of them.
One of the nice things about Waveforms Live is it's up and live right now at waveformslive.com. And you can add a simulated device. So even without hardware, you can start playing around with the user interface and generate some signals and play around with cursors and math and stuff like that. So we've already been getting feedback just with the simulated devices, which is great for us to have more eyes on it and more feature requests and things like that coming in. So we're going to be working on that. Keith has gotten distracted. We've been talking about Kickstarter stretch goals, and we're thinking about doing a Bodhi plotter as one of our stretch goals.
Okay, so I'll describe this a little bit. So this looks like this is a square wave that appears to be generated from our waveform generator.
Right.
Okay, but actually it's not a square wave. It's almost a square wave. A square wave is the sum of all the odd frequencies of the base frequency at a attenuated rate. This red line is the FFT of all the frequencies that are in that square wave. And what we're thinking about doing is we'll make one wavegen buffer that appears to have a square wave in it, and then we'll go ahead and apply that to the circuit under test, and then read in from the ADC what we get back, and then run it through an FFT and compare it to the square wave that we produced, and then compare it to what we get back, and the difference will be a frequency sweep or Bode plot of the circuit that we're measuring. So we can, so if you have a low pass filter, you'll see the breakpoint at the cutoff frequency, and that.
So yeah, so the simple version is basically imagine you have some circuit and you provide some stimulus to it. So you put some signal into it and you'll get some signal out of it. And you want to see what the frequency of the input has, like what effect that has on the output. So you can imagine that you start with like a 1 kilohertz signal and you run it through and measure the output. And then you go to 2 kilohertz and 3 kilohertz and 4, like all the way up to a megahertz, say. So you sweep through all those input frequencies, and then you want to see how strong basically the signal is coming out the other side. So typically you do that by actually writing out each frequency and measuring the response all in a row. And Keith has been playing around with the math and thinks that he can do it much faster. With the method.
Basically in one sweep instead of multiple sweeps. Well, it's kind of fun to play with it. And that is my distraction.
Awesome. So that's a stretch goal.
That's one of the stretch goals. Yeah, the other stretch goal is true bona fide data logging. I think we're gonna have to work on exactly how that works out. Right now, go on, Sam.
Well, yeah. So we have there's an SD card, like a micro SD card slot on the OpenScope. So that has kind of two nice side effects. We can actually take the Waveforms Live browser software and load it directly from the OpenScope. So even without having like anything installed and no internet access, you could take your browser on your computer and type in the IP address of the OpenScope, and it just loads Waveforms Live right from it. The other thing is then if you have an SD card, we could, we can save like calibrations and things there potentially, but we could also log data there, which is not something we really intended to do off the bat, but we've kind of already gotten feedback that that's something that people would like to do. So we're kind of kicking around ideas for how that might work.
Yeah, that would definitely be useful for like a remote setup where you've got like just like a Pi in the field, and then you can like grab all the data from all. Back.
Yeah. Yep. Like Keith has some solar panels that he wants to instrument and monitor over time, so it'd be perfect for that kind of thing.
And my well pumps. And how much water I've got in my tank.
Super cool.
I guess the last thing I'd probably say is to check out our Kickstarter for the OpenScope. So we're going to post some stretch goals there. So make sure to check that out. And then if you visit forum.digitalinc.com, we have a section there for feedback on the OpenScope. So we love to get feedback, have people start playing around with the software, and eventually we'll be posting all the source to all this stuff, and excited for people to start hacking on it and adding to it and collaborating with us on it.
Awesome. We'll post those links underneath this video, so go check out the Kickstarter and the demo software. You can get started and leave your comments. Thanks for joining us, and good luck with your Kickstarter.
Thank you very much. Thanks for having us.
Okay, bye.
Cheers.